I just wanted to ask a quick question.
Mm-hmm. Mm-hmm.
Can you remind me what it needs to be about?
So I will give you a full syllabus, not next week, but the week after. And I think that the video assignments will also end at that point, so you can spend the last few weeks totally focused on it. Um, the basic gist of it, we'll just go with that. The basic gist is that there is a central crisis at the heart of astrophysics and cosmology. Hopefully you guys have figured that out by now. Um, what I want you to do with this final project is actually look at one piece of that story. Maybe you look at black holes, or you look at, maybe you look at some structure on the surface of the sun, something we've talked about. You pick out one little piece for which there's two different possible stories. And you have the liquid sun story inside of a paper that I posted for you guys a while back inside of Moodle. So you can find a little piece of that. And what I want you to do is to go into and research the standard story about that little aspect. And I want you to research the liquid model of that aspect and compare and contrast them. And yeah, try to defend both pictures. And then, I'll be curious to hear how you guys synthesize your ideas about that as well. Kind of makes sense? Cool. So you'll have a full grading rubric and all that stuff that you need in a couple of weeks. Next week, I'm going to put up the creativity project. I was talking with B about that. If you guys do something creative, I hope you do, and I think you almost all do something creative. I don't know what it is. Maybe you cook, maybe you sew, maybe you paint, maybe you make music. Do something, sort of steer your creativity into something. And that is a really cool opportunity, I think, for you guys to make up any, if you've been missing some quizzes aren't going great, whatever. It's actually worth a fair amount of points if you put your back into it a little bit. And I just will give you credit based on how much effort you put into it, basically. It's very nebulous, but it's a good opportunity for you guys to bring your grade up. Um, there's no reason for anybody to fail this class. Like I said, last semester, almost everybody either failed or got an A, so just don't fail. It's really sad and a waste of money and time and everything. So do your assignments, do the creativity project, think about the final, think about some aspect of what we've been talking about. I'm going to keep going with all this. We're going to keep coming up against how there's two stories at every branch of this course, depending on whether the stars are condensed matter or whether the stars are balls of gas, right? So we'll continue to make sense of that, and I want you to ask questions. You can also send me ideas too if you guys are thinking, well, I want to talk about this, I want to talk about that, but I don't know where to look to find any research about it. So you can email me, you can come talk to me after class, talk to me before class. Cool. All right. So yeah, I guess I just gave it away, but I'm going to ask you guys anyways, what's the central crisis at the heart of cosmology? And yeah.
Whether the sun or stars in general are gas or liquid.
That's right, yeah. So, and then, who cares? Why does it matter? We're gonna get really fast at this. Everybody's gonna be able to do this by the time we leave, yeah.
So we know how to replicate the Earth.
Yeah, for energy, right? That's a good one to start with. Two other reasons that I want you guys to walk away from this class understanding. What's the other reason why it matters? Why does it matter to astrophysics? Yeah, right.
It helps to like solve or like change the answers to other questions we have in astrophysics.
Yeah, can anybody yeah, that's true. And we haven't totally gotten into those. We just finished last time building out this stellar classification diagram. It's called the HR diagram, named after these Germans. And we will get into each little piece of that in terms of how the story is told across that diagram for the lives and deaths of stars. And you'll start to see very soon how we get two very different stories for the lives and deaths of stars. I kind of previewed it. Does anybody remember anything that I hinted at might change about the downstream story of the lives and deaths of stars in terms of whether they're gases or liquids from last time? What's the main difference between gases and liquids functionally on Earth? Yeah.
Density?
Yeah. And so, but yeah, even more so, like what can we do with them? Yeah.
Water.
Contained. Yeah, that's a really interesting function, right? So if you squish water, you can, what happens to it? And this is kind of a trick question. I mean, have you ever filled up like a balloon with water and you squish it? Where does it go? How about this? If you had well, I'm kind of beating around the bush. Point is, when you squish liquids, they got to go somewhere else, right? Because you can't actually squish liquids, is the thing. They're not elastic. They don't compress, right? Now, gases, on the other hand, they're completely compressible. In fact, the way that we model gases is really simplistic. We treat them as if they are indefinitely compressible, actually, right? Which is totally insane, I know, but it's an idealized form of the gas laws that's quite functional, because you can squish gases. Now, what happens, generally speaking, when you compress gases beyond some limit?
You're referring to the light splitting thing?
I'm just talking about the phase. Like, what happens when you squish a gas?
It just squishes in fluid.
And then what happens in reality?
We can't squish anymore.
What will happen to it? Yeah, Owen.
Explode.
Yeah. Well, sometimes. I mean, I'm not laughing at you. I'm laughing because
Oh,
yeah, I mean, this is true that actually, like, certain liquids are combustible. It is absolutely true. That is one possible outcome. What else happens sometimes? Oftentimes,
they turn into a liquid.
they turn into a liquid. Yeah, they condense, right? So the atoms can't get away from each other. They often will bond with each other when they're confined to a smaller and smaller space. And so in the laboratory, when we squish gases, they turn into liquids. In classical astronomy, let's say the last century of astronomy, what happens when you squish gases is they stay gases, apparently, which is really, really bizarre. So what I'm trying to hint at, and I'm going to build out this story a lot more, is that when you squish the gaseous stars, they just keep squishing and keep squishing. And eventually, you can end up with something that's very, very bizarre and strange. And this will lead us into the story of white dwarfs, neutron stars, black holes, right? These are all the natural consequences of squishing a gas indefinitely, essentially, right? Whereas with a liquid, you can't squish them. I mean, you can squish them all you want, and interesting things might happen. But they will hold their form, ultimately. This is a very, very different aspect. So, if you're looking, here's another thing that we talked about I want you guys to take away. If we want to make a ball of gas, a gaseous star, dim, but hot, we talked about this a little bit. How would we do that? This is kind of follow-up from the last question, the last thing that I told you. Yeah.
Change what it's got going inside, what it's fusing, and what it is. It's like elemental makeup.
Yeah, so I probably asked that question wrong. If we see something in the sky that is very hot but very dim, what can we say about it under the gaseous model? Yeah.
White dwarf.
Yes, indeed, white dwarf. But so let's say that a white dwarf is a very hot and dim star. How do you account for that in a gaseous model? Yeah, it's little, right? Because the only thing that we have available to make it dim, barring structure, remember gases don't have structure, so barring structure, we can't change the optical properties any other way than making its radius small, right? That's the only way we get something hot that's a little tiny pinprick of light, but it's still temperature-wise very hot. With the liquid model, what kinds of things can happen in order to change how bright it is? Diamond, soot, what's the difference?
Structure.
Structure, yeah, just the arrangement of the atoms, right? This can wildly change the optical properties of condensed matter. This is really important. Condensed matter is liquid and solids, right? Okay. So there's going to be very different stories that we tell about dim lights in the sky based on whether the stars are liquids or gases. It's going to matter more and more as we start looking at some of these exotic objects that are very difficult to explain otherwise. The white dwarfs being one of them, the more extreme versions being the neutron star and the black hole, which we will play with very soon. All right, so what's the third reason? Who cares if the astronomers have the stars all wrong? Why does it matter for everybody else other than fusion energy? What else? Why does it matter? Come on. Who cares? Who cares if we're thinking about all this stuff all wrong?
Every other answer to question about space.
But what about beyond space? Who cares? Why does it matter if you're thinking about the sky all wrong?
In science, as we know, to be consistent.
That's exactly right, yeah. So science is, you know, it can be quite tyrannical or it can be extremely liberating as a practice, right? It's tyrannical if things don't make sense and somebody says that it is so. It's liberating if it makes sense and you can understand how it makes sense and you can use that knowledge productively in your life, in your civilization. And if we have a science that doesn't make any sense, that's perhaps threatening to the entire project. Does it make sense? Write it down. I'm going to ask you guys again every single class at the beginning, and we'll hopefully spend less and less time doing this because I need you guys to understand these three things. Fusion, the story of the lives and deaths of stars, and the global impact of having a consistent science that actually makes sense to people, not just mathematicians. Okay? This is super, super important. Okay, so other than that, help me stay awake, guys. What remind me what happened last time? What's going on with stellar classification or any of this stuff? What did we talk about? What happened? Anything you remember from last class? You guys don't remember a single thing from last class? It's 2 days ago.
Yeah, with the HR diagram.
Okay, we were playing with the HR diagram. What else? What were we thinking about with the HR diagram, or what else were we doing? Yeah.
We also saw like all plants fall along the main sequence.
That was really interesting. Yeah, so you can plot the brightness in terms of non-visible light, but even the planets can fit onto the HR diagram, which is really, really fascinating. And we'll circle back around to what that might mean later. Yeah.
Talking about measuring distance between bodies through angles.
Yeah, I think that was important.
Mhm.
So we were trying to wrestle with how you tell how far away something is, particularly a point of light, right? So you can't actually measure the angular radius of a point of light. It doesn't work, right? Because it's diffuse, right? You can measure the angle of the moon or of a planet because it's actually got a pretty dim surface that's not going to prevent you from seeing what's going on. You can't do that with stars, right? So how do we see how far stars are away? How do we know? Or how do we think we know? Or how do we even estimate how far away something is? Yeah.
We take. Oh God, it had a name.
It's okay.
As we travel around the sun, we take observations of a star at two opposite points.
Nice.
Parallax, right?
Parallax, that's it. Yeah, so this is kind of like the close one eye, close the other, move your finger, you can see it moves in position, right? So you set this baseline, it could be your face, or it could be a huge baseline the size of the whole the whole orbit of the Earth, essentially. And you use that to find the tiny little angle of separation that star appears at, right? How your finger actually moves. The angle, if you chop up the whole room, let's say into 180 degrees, you can see the angle from which your finger moves, right? It's the same thing with stars. Now that's pretty cool. That's actually the best, most reliable way that we can tell the distance to stars, right? But what's the problem with that? Or how does that let us down eventually? Yeah.
too far away, the angles will collapse.
Exactly, yeah. So if it's really far away, beyond a few hundred light years, we can't actually resolve any angle, right? There's the baseline that we have in our orbit just isn't big enough, right? Okay, so that's interesting. So how do we fit, so what do we, I'm not sure this was clear, it's my fault if it wasn't, but how do we, what do we do with stars that don't quite fit onto that, that are too far away, let's say? Kind of hinted at some of this. There's a couple of possibilities. Talked about a couple of them. We have to start making some assumptions, right? So I kind of cracked open this idea of standard candles at the end, right? Does anybody remember these pulsating stars we talked about? A little bit nebulous though, right? It's a little bit tricky. So there's some pulsating stars. We talked about some called the Cephids, right? And the idea is that, these are kind of reproducible pulsations. If we can actually, through parallax, locate one of these pulsating things, then if we see the same kind of pulsation somewhere else, we can infer from, how its luminosity is decreased, or sorry, how its, its apparent brightness. We can sort of infer the distance to it, right? But what's the problem with that? Anybody remember? Problem is, sometimes pulsating stars look like they're the same kind of pulsating stars, and they're not, right? This was a huge problem early on when they tried out this method. They actually confused two very similar types of Cepheids for each other, and they had to recalculate their distances to their entire star map locally. They were actually off by a factor of 200%. So they had everything kind of off, right? So this is tricky, and this is honestly, things start to get really, really weird after we get outside of the direct parallax measurements, because we're starting to construct what is known as the distance ladder, and we're going to come back to how we do this for things that are really, really far away. But we have to have some sort of standard candle like this, and whenever we think we have a standard candle, we run the risk of sort of being wrong about that. So, okay. We'll come back to the HR diagram and the intensity, the luminosity intensity situation. By the way, what's the second way? Sorry, I just put some math up here to scare you, but we'll come back to that in a second. What's the other way that we fit stars onto that diagram when we can't tell where they should go because we can't measure the parallax? We don't really know how bright they are because we don't really know how far away they are. How else do we stick them onto there? Yeah.
By estimating surface temperature.
Exactly. So we say, oh, this thing is this temperature. Maybe it's got these lines in its atmosphere. So we think it's this kind of star. For instance, let's go back to our little diagram. We think this is it's very hot. It has some certain lines that make us think it's not a nearby white dwarf. Maybe it has a partner or something that makes us think that, okay, we can just place it up there on the HR diagram, which means we know, or we assume its luminosity, right? And we can back calculate the distance because now we've assumed its luminosity. We know how far away that candle is, right? Based on how bright it is. So that's interesting as a way that's a pretty bundled set of assumptions. But what's the problem with this as it concerns the liquids versus gases? This is where things start to get a little bit weird, and this is why I put this equation up on the board. I already asked you guys this, so I'll just make you repeat it. So what factors might contribute to the loss of luminosity in the case of liquid stars? Yeah. Yes, but that's not quite what I'm reaching for just yet. We'll get to that. That is absolutely true. Carbon, diamond.
Makeup.
Yeah, the structure, right? The actual bonding arrangement, right? So this is, in general, to put those stars on that HR diagram, we assume this luminosity value, right? And we say that it's proportional to the 4th power of temperature. It's proportional to temperature, let's say. The real Stefan-Boltzmann relationship that allows you to make that calculation actually has this really important term. This is little epsilon thing. That epsilon specifies how much of that light can be converted into heat, and heat can be converted into light. This is well-known property. So all materials from graphite, everything that emits light from heat in a laboratory on Earth, everything we've ever seen, does it with varying degrees of efficiency, right? So it's not perfect. Even the best black bodies we can make in the laboratory that are really, really good at turning heat into light and vice versa, they're not perfect. So they're scaled by this little term in the equation that it's somewhere between 0 and 1. If they were perfect, it would be 1. Now, the gaseous star proponents treat it as if it's a gas. It has an emissivity of equal to 1. It's a perfect emitter and absorber in their models. But with real materials that have actual structure, like condensed matter stars would be, you actually have to start thinking about how the structure is changing its efficiency, its ability to convert heat into light. So that luminosity can start to drift wildly. You can actually have something that's much, 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 much less bright. Not simply because it's smaller or there's less of it, but simply because its structure is rearranged, right? Diamonds and soot, they are made out of carbon, pure carbon, both of them. They have very, very different optical properties, okay? All right. Skip that for now. All right, we're going to come back to the HR diagram here because we need to talk about, the HR diagram is going to make sense when we start talking about the whole lives and deaths of stars. But I believe Evan asked last time at the beginning of class about what kind of stuff goes into making a star. How do we actually get that? So I figured today would be a good chance for us to catch up on the stuff that goes into making a star, because the next thing we got to talk about is the stars being born. And then we got to talk about how stars die. And there's very different stories about that on each side of the camp. With liquid stars versus gaseous stars, very, very different stories get told. But fortunately, they seem to have the same starting materials. So that's really nice, right? So this might be the least what would we say, controversial lecture of this entire course, I suppose. Because the stuff that we see in between the stars is presumably what the stars are getting made out of. And we can all pretty much agree on what's in between the stars. And there's a, it's actually quite a complex soup that's out there. So interstellar space is shockingly full of atoms, actually. So I want to go through a couple of different possibilities here. So we'll talk about what this stuff is. We need to talk about this concept of ionization because we haven't really talked about it yet. And we need to talk about cosmic rays because they're kind of another little piece of this puzzle. In general, the stuff that's out there between stars, we just call it the interstellar medium. What's a medium? You guys ever heard that word in the context of science before? It's just kind of, yeah, go ahead.
Like a starting point, like a plane of existence?
Yeah, it's kind of the backdrop, right? So, I remember like when, if you ever work in like a biological laboratory, you grow cells on some sort of soup, they call it a medium, right? It's kind of the backdrop upon which things take place. So the medium is really the stuff that's out there that isn't the traditional luminous bodies, the stars and planets and all of that. It's everything else, right? It's all the junk that's lying around in between, right? So we just call it the interstellar medium. And so I want to start thinking about what exactly that stuff is, and because if we can understand what that stuff is, we might be able to come up with a sane story of how the stars just kind of happen. Presumably they just happen because there's lots of them everywhere. And, we can't actually see them being born, but we know that there are stars that look like they're in various stages of their existence. So how does this happen? So, anybody know what this thing is?
An amoeba?
Good guess.
Um,
It's a piece of dust, actually. A piece of dust. So that's a micron. Does anybody know what a micron is? How small a micron is? You guys know what a millimeter is?
Sure do.
So a micron is 1,000th of a millimeter, okay? It's about the size of maybe a bacteria or something like that, right? So this little scale bar you see, it's about the size of bacteria. This is a piece of dust from interstellar space. Presumably somebody snatched it up in a spaceship at some point, right?
Wow.
So this is actually an extraordinarily complex structure. I think you would agree. I mean, it's not a gas molecule that's just bouncing around. It's got some form to it. It has structure to it. And when we start looking, we're going to actually, hopefully by the end here, reconstruct exactly what this is. But needless to say, interstellar space is teeming with this kind of junk, actually. So that's really interesting. So there are these condensed matter structures that already just seem to be everywhere in interstellar space. And this isn't just a homogeneous piece of junk, right? It's got lots of different molecules part of it. We're going to see that there's ice that's part of it. There's carbon, which is part of it, right? There's all sorts of really interesting pieces to this puzzle. So this is actually a very complex structure that happens to just kind of be everywhere in interstellar space. So that's interesting. All right. And it's not even the thing that is like, to be clear, there's a lot of this stuff in interstellar space, but this is probably only 1% of the stuff. The rest of it is truly individual molecules or gases that are out there. Most of it's hydrogen, just like the stars are mostly hydrogen. Most of the stuff that's floating around in space is hydrogen too. So let's look at that. You know, how thick is this stuff? How much is out there? How much interstellar medium? Like, what's the density of this? It might kind of surprise you. How many atoms if I go and, you know, take a little jar? 2 atoms. How many? Yeah, let's say I have a little centimeter vial. This is cubic centimeter. How many atoms?
Many thousands.
Just one, actually. Yeah.
I was so close.
Yeah. Yeah. But that's actually a lot if you think about it, right? It looks quite empty in space. But if you think about it, there's actually, for every centimeter of space, there's at least 1 atom there on average in between stars, right? This is like outside of the solar systems of them, right? So, I'm just showing you guys some pictures of these things. So these are all illuminated gases that we're looking at here, which is kind of interesting. So all this fuzzy stuff that you see, these nebula that we see in the sky, we get these beautiful pictures from different telescopes of these swirling balls of gas. Why do they have these colorful lights associated with them? Yeah.
They chemical reactions to either other atoms or temperature.
Yeah, that's a great answer. They are reacting to their environment, right? What were you gonna say?
I was going to say they were absorbing like energy from, well, like suns, and then
Yeah.
for that energy, that's what they will glow with.
Yeah, exactly. So, you know, we've talked about there's this basic principle of light, let's say, which is that if you absorb some light, you're an atom, you absorb some light, you can also emit that same light, right? And sometimes it gets transformed in different ways, and maybe you emit a different kind of light. That's possible too. But you can, at the bare minimum, emit the light that you receive. And so, what is energizing these things? I guess Ethan just kind of hinted at it, but in some sense, there's a lot of stars around that are pumping a lot of, for lack of a better word, they're pumping a lot of light into these clouds, right? And I think cloud's a good way of thinking about them, actually, right? Because it's a mixture of condensed matter and gas. But the gas is glowing, and it's glowing in these very, very beautiful colors. These are actually somewhat true to form. So assuming that most of these clouds are mostly hydrogen, you know, if we take a tube of hydrogen, this is like a little light bulb basically filled with hydrogen, and we run a current through it. The hydrogen glows, actually, right? It's being electrified, and the hydrogen glows, and it gives off, predictably, individual lines of color, right? Doesn't give us that nice prism rainbow, but it does give us a few different lines. So as the hydrogen as these atoms are excited, they give off this light. That process where they actually get excited is called ionization. And we need to talk about ionization a little bit because it's kind of weird. What could drive it? So you mentioned this other light. So you could shine a star itself can shine light onto these hydrogens, and they can get excited, and they can release light. What kind of light would be most effective at that? I don't know. I don't expect you to know the answer to that. But stars give off a lot of light, right? What's the most powerful? So even our sun, what's the most highly energetic light that the sun gives off? Yeah. Oh, that's actually true. It does occasionally give off a gamma. So remember that distribution the black body distribution of the sun, right? It's this big curve. It's kind of we've got the intensity over here, the luminosity, let's say, and we've got the wavelength on the x-axis, right? So red stuff down there, blue stuff down here, and then we have a nice curve and all the visible lights up here, right? Gamma rays would be way invisible, basically the bluest light imaginable, right? But what about this stuff over here? It's actually a fair amount of intensity down below the visible range, right? It's too blue for us to see. What do we call it?
Ultraviolet.
Yeah. So there's a great quantity of ultraviolet light being emitted, and ultraviolet light happens to be the exact kind of light that excites the hydrogen, actually, right? So you can do it by driving a current through a discharge, through a tube filled with this stuff. That's one way to do it. You can also shine a light on the hydrogen, and it will be excited, and it will emit this beautiful red, pinkish light in return, right? So that's one of the biggest drivers. When we look at these beautiful clouds out there, and we see this reddish glow from these enormous, huge, massive clouds of interstellar hydrogen, one of the things we're seeing is those ionized or overdriven atoms that are relaxing and giving off this beautiful pinkish light. So that's really nice because, well, if we want to go looking for interstellar medium, we can find some of it, right? Because any of these clouds that happen to be next to a big star that's giving off lots of UV light, they're going to shine with this particular signature, right? Now, that's nice for clouds that are next to stars, but it's going to be a problem for other stars. By the way, this ionization thing, has anybody ever heard of it before in another class, maybe high school, chemistry, anything like that? Yeah, so that's okay. How did your teachers talk about it in terms of chemistry and stuff? Do you remember? Anybody?
Didn't really understand it.
Yeah, probably not. Yeah.
Things become like charged.
Okay. Yeah, absolutely. It is a charge separation. So it involves this word. So another word for ionized gas is plasma. You guys ever heard that word before?
Yeah.
Well, the sun is alleged to be this plasma thingy too. So it's another word that we maybe flirted with but didn't really totally break down. So if you take any other science class on Earth, you'll probably hear that plasma or ionized atoms, what happens is that the electron gets ripped off of the atom and the charge, like the electrons are totally disembodied from their atoms. If it's just a hydrogen, it only has the electron and a proton. So the proton's somewhere, the electron's somewhere. So the idea is that there is this, it's so energetic that the atom is sort of ripped apart or something like this, right? Now, I'm not sure how awake everybody was for this, but I have expressed to you guys many reasons why that's an untenable proposal. I've expressed, I believe many times in this course, that I think that treating the electron as if it is a mote of dust is a little bit silly and is actually not reflective of everything we know about electrons, which is that they're actually an activity. Right? There's a dynamic associated that we call an electron. It's a dynamic associated with the electrical action of the atom. So if the electron is just an activity and the proton is another activity that the atom is doing, how do you rip an activity? How do you rip this activity off of an atom, right? Well, you can't, obviously, right? So, oh, by the way, this is kind of the standard picture of ionization, right? This little electron just kind of gets ripped off, it's flying around, whatever, right? So, there's another way of thinking about this, right? So this is something that's really quite interesting, and it feeds into what I was just talking about with the fact that there's only one atom per cubic meter, or cubic centimeter on average out there in interstellar space. So one thing that people have found, which is really, really shocking, is that when you depressurize an atom, when it's not in the atmosphere of Earth, let's say, when it's in a vacuum, a really, really strong vacuum, you pump all the air out of it, and you just leave an atom behind, right? Turns out that the atom actually occupies an enormous space. Enormous. Like on the order of centimeters, actually. So the atom expands, actually. And we don't know to what extent it expands, but it seems like it expands enormously. Certainly on the order to fill that cubic volume that we just spoke of. So what's really interesting is that you can actually take a vacuum tube, let's just say like a little jar basically, pump all of the air out of it, and apply an electric current to it, like in that drawing that I showed you before of the hydrogen spectra, and it will actually become conductive all of a sudden. Neutral hydrogen, you pump all of the air out of it, except for there's going to be a few atoms left behind, right? And all of a sudden, those atoms are able to conduct between the anode and the cathode, right? Now, this has actually been a super useful technology. So when I was growing up, almost all of the TVs used this technology. They had these huge vacuum tubes inside of them, and they would have a current that was arced between the back of the TV and the front. And they would use magnets to basically draw something on the back of the screen using this exact same principle, right? Now, the conventional explanation for that was that these little electron bowling ball thingies are getting shot from the front of the tube to the back of it, right? And the magnets are pushing them around and stuff. But with everything we know about the atom, it's also equally possible that what's happening is that the atoms that are left in the tube are being depressurized to the extent that they actually expand quite a bit. And they can actually function as a wire between the front and the back of the tube. And then you push that single atom wire, maybe it's a couple of atoms across, I don't even know. Maybe you push that thing around with your magnets instead. So I think there's a material explanation for ionization, which is responsible for all this beautiful light we see. There's a material possibility that those atoms are acting as wires amongst one another. They're literally in contact with each other, and they're conductive. They're getting excited, and they're passing that conductive excitation along to one another in a big chain of relay. And so what we're actually seeing in the sky is something very similar to those vacuum tubes, right? Something very similar to a bolt of lightning. Have you guys ever, you've seen lightning, right? Well, now, what's interesting about, what's up with the shape of lightning? What does it look like?
Bent.
Kind of all bent and stuff, right? So it's interesting, you can actually do that in a laboratory on Earth. You take a chamber full of air, and the same thing as our vacuum tube, except it's not a vacuum. It's not empty, right? It's got a bunch of air inside of it, like our atmosphere. And you turn up the current at the anode and cathode, right? So really drive the one side of it. You drive that negative terminal really hard. It's really charged up, right? Eventually, the air will start to break down. So individual atoms will actually start to get ionized, and they start to explore different pathways to get to that sink at the other end where they can relax and give away their electric excitation, right? All that motion that's happening at the surface. A funny thing happens, though, when you start to pump the air out of your little experimental lightning chamber. What happens to the shape of that branching lightning? Anybody? Any guesses? Well, there becomes less and less paths available for it to explore, right? It starts to just narrow, and eventually when you pump down, you get as much air out of it as you can, which, by the way, you can't really get rid of that much air. It turns out it's very, very difficult. What happens is it collapses into basically a single wire, a single plasma wire, basically, right? This is called a cathode ray, actually. This is what the early experimenters gave the name to it. And they found, of course, that you can push this single atom wire type thing around. You can push it around with magnets, right? So, two very different pictures of what's going on during plasma and ionization, gaseous plasma in this case. Plasma is a horribly ambiguous word, though, unfortunately. So plasma really just means that your charges are liberated. And of course, plasmas can be liquid, plasmas can even be solid. So technically speaking, a metal, just a regular old metal, like this microphone or something, technically has, it is a type of plasma because it has delocalized electrons, which is crazy because it really just kind of speaks to how I don't want to say useless, but how painfully broad that word plasma actually is. But we're talking about gaseous plasma, right? So formerly neutralized gas that's now capable of perhaps expanding, perhaps the atoms can actually conduct electricity, they can do new things all of a sudden, right? So I'll see if I can dig up a video of this for you guys for next time, because it's really cool to see the light, these chambers go from having lightning branches and then seeing the air pumped out, and it narrows down into this beautiful little wire, basically, this glowing little plasma wire. Very cool. Okay, so what do we do if we're trying to say how much stuff is over here when we look out into space, but there's no stars around? There's no UV radiation to light up our hydrogen. How do we know if it's there or not? Well, there might be other stuff besides hydrogen in smaller quantities, right? So at the beginning of the class, I was like, yeah, this is a piece of dust. It's got a lot of stuff in it, right? So we might get lucky and we might find other absorption lines. So we might be able to see a star that's behind it, and the star behind it, again, based on various assumptions and stuff, we say this type of star should have this kind of atmosphere. But now we see new little absorption lines, right? So something in the middle is eating the light. And so we might be able to find non-hydrogens, right, that are actually absorbing that light. So hydrogen's not going to eat it. Like I said, this hydrogen, this beautiful glow, comes from this UV light. If there's not a lot of UV light nearby, maybe we can see some other atoms that are getting eaten. There's another way, though, too. And I didn't realize this was going to be such an atomics-heavy discussion. But there's one other thing that we actually found. So we have to talk about the electron a little bit more. So people came up with, basically people empirically realized that neutral hydrogen at some points gave off a particular kind of light. It was really, really weak light. It's actually radio light. It was so weak that its wavelength was on the order of centimeters. It's a huge, huge wave of light, right? They actually called this form of light the 21 centimeter line. Now, they wrestled with how to explain how in the world an atom would be able to do this, especially these individual atoms out there in space would be able to be so low in energy that they could actually give this kind of light. And they came up with this mechanism, which is in your textbook. I'm not sure if you read it or not. It's called the spin flip mechanism. This is interesting only because spin is kind of a fun concept to play with. So if you guys ever, I don't know, maybe you took chemistry in high school or something, you may have come across, you probably didn't, but you may have come across this idea of electron spin before. Anybody ever heard that concept before? A little bit? Do you remember anything in particular?
Not too well of it, but I know it had some interesting implications on certain atoms.
It's a really, really weird concept that has been really, it's a piece of the mathematical atom that deserves paying attention to, actually. So, I mentioned probably from day one that we don't really have a material atom in physics today. Although people have pursued them, they kind of gave up in the 1800s for the most part. We have a mathematical atom. And so this is called quantum mechanics. And our quantum atom allows us to make predictions about how our atom is going to behave in different circumstances, right? And it's all bundled into this really powerful piece of math, which is called a wave function, ultimately. And one of the attributes that falls out of the wave function tells us about the way that the electron rotates. So I already have told you guys in this class and many other times that the electron is a dynamic, right? It's an activity. It involves motion. So the electron has intrinsic motion, which is called angular momentum. So it's moving, it's spinning, angular momentum. It's spinning in a certain way. And all measurements of electrons have this conserved quality to it. The weird thing about that motion is that it's not spinning like a basketball, all right? The spin of the electron has a strange symmetry where, if I took a basketball and I put my finger on it, on a point on it, or I just draw a point on it, and I rotate it, after 360 degrees, it will be back where it started, right? That point, I can just rotate this and it'll come back around, right? What falls out to us from studying this predictable behavior of electrons in the lab is that we actually have to rotate them twice to get back to their starting points. Okay? So this is often illustrated like this. I was hoping this GIF would work, but it does. Oh, there it goes. Nice. So here is a weirdo little system that you actually have to rotate twice to get it back to its starting point. Now, this famous mathematician named Paul Dirac developed an entire form of mathematics to handle these kinds of weird rotations that require two rotations to get back to their starting points. Needless to say, nobody had any interest in a physical atom at this point. There was no material atom. And so this concept of the angular momentum of electrons, the intrinsic motion of electrons, was relegated to being a pure mathematical abstraction. Yes, we can measure the angular momentum of these electrons, but it's not a real thing, because how in the world do you rotate a little point particle and have it require two rotations to get back to the same starting point, right? Well, it's interesting because this has become a very observable effect. So the actual changing of this spin gives us radio light, in fact. And that is the 21 centimeter line that we use to actually see neutral hydrogen. So we know that this is a thing, we can measure it. It falls out of all of the predictive mechanics from our quantum wave functions. spin is a thing, but the quantum mechanicists say it's not a real physical quality. Yeah, it's an angular momentum, but there's no way to actually solve that for an atom. I don't think that that's true, actually. So I think, again, if we think about the atom as actually having a true surface, and the true surface does in fact rotate, however, it sort of folds back through itself at the poles, right? Then we have an opportunity for the surface to actually rotate twice before that point can pass through its center and return to its face. This is not only a material picture of how this could happen. Let me see if I can play that again. So looking at one that's spinning upward and one that's spinning downward. Not only is this a material process that gives us a surface which rotates twice to get back to its starting point, but it's also really similar to another phenomenon that we've talked about in this class. Let's see if I can find it. This one, right? Especially when we start talking about why in the world would neutral hydrogens be inverting their spin periodically on their own with no stimuli? Well, if the actual atoms are not perfect spheres, if they have any sort of asymmetry to them whatsoever, then we know that objects that are spinning in space with asymmetry periodically invert their spin. This is a natural consequence of the intermediate axis phenomenon. Tennis racket problem. This thing that the Russians thought was going to destroy the world. Yeah.
That has to do with like magnetic stability, the same way that the sun and the earth changes magnetic force.
It is related to the changing of the motion as a hypothesis for what might be happening inside of and leading us to have reversals of magnetism. I mentioned that earlier. Now people argue nonstop about what causes the magnetic reversals. It's certainly not an established idea, but it is tantalizing that spinning objects really do naturally invert their spin. And so if electron spin is truly the angular momentum, it's not just some artifact of math, but it really does represent the spinning motion of the surface of the atom. And it moves in any way similar to the way that I animated it for you with this little blue surface, which involutes on itself. Then we have good reason to believe that those atoms, when left in space, will actually invert their spin naturally. And maybe this is why we get the 21 centimeter line. Maybe this is how it happens. Very, very slowly, these things actually do naturally invert their spin. So this is, these are actually the first guys who detected the 21 centimeter line. And it's turned out to be one of the only ways that we can see neutral hydrogen in space, and so that we actually know that there's a lot of stuff where we otherwise don't see things glowing. So all of this is kind of going into a picture that the world around us outside of our solar system is actually chock full of activity and things happening, even if it's not glowing in a nice visible way that we can see. So, by the way, those places that are glowing, they're reported to be, so in order to, this is, whenever we start talking about temperature, things get kind of weird because temperature is a pretty poorly defined idea. But those regions where we actually see the ionized hydrogen, right, the glowing pinks that I showed you at the beginning in those pictures, they're supposed to be tens of thousands of Kelvin, very, very hot, right? Hot as the atmosphere of the sun. Now, how is that possible, first of all? Well, the temperature concept is very strange because what it really, really comes down to is kinetic energy. So how much motion, right, is being transferred into a system. If you have one atom that's moving really, really fast, and you only have one atom in this volume, then the average kinetic motion, the average energy of that one atom is really, really high. So the temperature is really, really high. Now, if you touch that atom, is it going to burn you? No, right? So it's not hot in the way that you guys would think about heat, right? The reason that you think about heat the way you think about heat is because you're in these pressurized environments where there's lots of atoms, right? This is like getting hit with a sandblaster versus a single grain of sand, right? Okay, so when you see these temperatures being talked about in these interstellar nebula, we're talking about really, really thinned out, low density environments where the individual atoms could have a lot of energy, but and therefore technically their kinetic energy is really high, but it's not necessarily a really hot place, and that's a funny thing to deal with. All right, there's one final way that we can deduce where if there's hydrogen, but we can't see it. And not just hydrogen, but other molecules. And that is that molecules often occur in pairs, or gases, individual elements occur in pairs. So if we know that when we look at a luminous cloud and we can see the nice red glowing hydrogen, right? And then we notice that there's other elements, right? I talked about how you might be able to see the absorption lines from other things like nitrogen or carbon or something like that, right? We can establish what we think is a ratio of naturally occurring hydrogen to those elements, right? So maybe let's just throw a number out there, like there's one carbon that we see for every 4 hydrogens that we see. So what we can do, and this is a huge assumption blanket, but we can hope that if we go out and we see some carbons over here, or some nitrogens, that there are some hydrogens there, just because that's what we usually see when we can see the hydrogens, right? This is another way that people estimate how much hydrogen is lying around in different places. So, and this is really crazy ratio. Actually, the ratio is more like for every 10,000 hydrogen molecules, we assume that there exists a single carbon monoxide atom. And we can see carbon monoxide lines really, really easily. It glow in a very predictable way that we can see. So we just assume that there's 10,000 hydrogens lying around for every carbon monoxide. Are there? I don't know. But that's one of the techniques that people use. All right, let's talk about dust a little bit. So this is where we actually get into really complex structures for the first time. We start to see these things. So when people first started observing what we now know are dust clouds, this is what they looked like. And what did they think at first? Yeah, they just thought these were just big voids, right? So the stars would inhabit regions, and it was kind of like Swiss cheese, right? So, you know, with a bit more study, including a lot of the things we talked about now for seeing things that are not visibly apparent, but maybe we see 21 centimeter lines, maybe we see other lines coming through the back when we look at in non-visible wavelengths, we start to realize there's stuff there, actually. So there's a couple of ways that we can know for sure that this is dust and not just Swiss cheese in the night sky. One is how they block out the light, and so we're going to look at that. They also do give off, dust actually gives off light. What kind of light does it give off? What color? Let's assume it's pretty cold. So, not gamma rays. Infrared, yeah. It gives off really, really far red light. Light you can't even see because it's so red, right? So it has some emissive qualities to it, this dust stuff. So with the advent of infrared cameras, so we eventually were able to make sensors. Of course, the guys in the early days of the 20th century didn't have access to infrared cameras like we do today. They're sensitive to that red light, right? So we can see the actual dust in infrared now. And then there's the third thing that they do, which is they reflect light. So they scatter it in different ways, sort of like how our atmosphere scatters the light at sunset, right? So it gets very red. So we can see all of these things. So there's actually a lot of places where you would go out and look at a star that appears to be kind of glowing, right? And actually the glow around it is the dust which is scattering the light in all directions, right? And so when we start to image it in maybe the infrared, we can actually see that dust itself. But in the visible spectrum, we would just see kind of a diffuse halo, right? These are, I believe this is the Pleiades. You guys ever seen the Pleiades? It's a cluster of, this is, you should be able to see it pretty much all the time. Or it's not as easy to see as Orion we talked about last time, but it's a cluster of 6, maybe 7 stars, depending on which millennium of the past you were viewing it in. All of the ancients tell stories about the Pleiades constellation, and they always talk about 7 stars. We can only see 6 today, so a lot of people think that the one went behind the other, right? And maybe it disappeared for some other reasons. I think it's still there. You can see it with a telescope. I don't know. The point is, when you look at the Pleiades on a telescope, you actually see these really nice dusty clouds all around it, right? So it's a really good example of that. And you can actually see this with the naked eye if you go out at night. So this is the mechanism I was talking about. This is very similar to what happens at sunset, right? So, you know, what's the difference between scattering versus absorbing light?
Reflection.
Yeah, that's exactly right. Yeah, it's a kind of reflection, really. So gases are tumbling all over the place, right? So incoming, so like right now, I mean, there's a lot of atoms between me and you, so we can see each other. But you know, presumably there's a pretty faithful chain of relay of the light between your face and mine, or my face and your eyeballs, or however you want to cut it up. Now, if I put a ton of atmosphere in this room, some of that light is actually, because those atoms are all tumbling around and stuff, that incoming ray, as that atom tumbles, it's going to sort of shoot it off in the wrong direction, right? A very faithful reproduction of the incoming ray, but it's going in the wrong direction, right? It's a kind of chaotic reflection. I think reflection is really the right way of thinking about it. And a reflection is really just a transmission which is not directly in line of the ray itself, right? So this is interesting because the blue light tends to be the one that's scattered the most versus red light. I was thinking about why that is, actually. I mean, this is getting a little bit heavy and deep, but it's kind of cool. Now, usually science books and stuff just say that it is so. The blue light is the stuff that's scattered. The red light is not scattered. It is true. It is apparent. That's why the sky looks blue to you right now during the day, because the blue is actually from the nitrogen in the air is actually kind of scattering the blue light down, and it's reaching your eye and all of that. Why is that? Yeah, what do you think?
Is it because the wavelength is a lot tighter and a lot?
Yeah, I mean, that's definitely true. Why do you think that it gets cast about more readily than the big waves? There's no like right answer for this. I think that I mean I think we can make sense of it. I think there is a reason, obviously. What do you think?
With the tighter wavelength, it has more chance to hit something by comparison to red, something with a longer wavelength, since it has a larger sort of.
It's slower.
Yes.
How about it's slower? So if you think about your gas atoms as kind of tumbling around, right? As the wave comes in, remember we've talked about the wave as really redirecting the motion at the surface of the atoms, right? Well, as that atom's tumbling, it's tumbling at some speed. It might seem like it's really fast to you, but at the time scale of light waves, well, a really fast, short oscillation, the blue light, is going to happen during a turn of this atom, right? So it's going to be able to kick something off really, really quick. But the big waves, on average, all of those little tumbles might not matter as much because the wave is so slow that this thing, as the atom chaotically kind of tumbles around thermally in the gas, maybe on balance, that wave is just not capable of being completely re-emitted during any one of these tumbles. and you actually have more of a group effect of all of the atoms contributing to this overall transmission process. I don't know. It's just it's a thought. It's a very interesting phenomenon and very well defined in terms of observations, and the math is quite predictive, but the mechanics of it are sort of wanting. All right. So so we can lose some light to scattering. We can lose some light to absorption, I guess, in terms of the infrared. So what does this mean? It means that there's a process that happens where the light that comes to these dust clouds tends to be filtered. The general term for that is extinction. So the light is extinguished, I guess, that doesn't make it to us. The result is that these are very red and dark clouds that come across in our imaging. So what in the heck are these things made out of? These clouds, these dust clouds. What exactly is a piece of dust? Have you guys ever wondered what a piece of dust is? It's a little bit different in space. We know that dust, we can actually examine this stuff because there's tons of it out there, find pretty complex molecules. We find ammonia, methane, water. These are actually organic molecules, by the way, which was actually kind of shocking to people. So when I was a kid, not that long ago, feels like yesterday, they used to call these hydrocarbons, like methane and stuff, they called them fossil fuels, right? I don't think they call them that anymore, right? But they called them that because they thought that they only came from creatures that had decayed, right? So the only things that made these hydrocarbons were creatures. Then they started finding them all over space, actually. They started finding that they were abundant in the atmospheres of the planets in our solar system. Turns out you can actually get organic compounds through completely inorganic processes as well. So space is full of organic compounds, which is weird. It just kind of blows open what the word organic actually means. Basically nothing, but at this point, these little droplets, for lack of a better word, have lots of these organic compounds in them. And at their heart is what? What is this little thingy at the center? Well, it could be lots of things, actually. So it's something solid, though. That's kind of interesting. So unlike, it's not a liquid, it's not a gas, it's actually little solid chunks of stuff, right? Now, the most common kind of chunk is, well, let's start with the least common ones. I skipped over it. So here's a nice little cage of carbon, actually, a little ball of carbon, right? Basically, a little chunk of rock, for lack of a better word. You can have actually little dust grains that are carbonaceous. You can have ones that are silicate rich, so they're more like the kind of rocks that we find on Earth for the most part. You can also have the little chunks that are made out of solid water too, right? Ice. So you can build up here's another question. How in the world do these complex molecules survive all of that radiation and stuff that they're getting pummeled with? Because usually, if I take like some water, let's say water vapor, and I subject it to UV radiation, what happens?
Thumbs up.
Yeah. What else? But yeah, I mean, definitely. But what will happen if it's just some water gas and I just shoot it with intense UV radiation? The answer is like it will break apart into its individual atoms eventually, right? It's just called hydrolysis, right? So the oxygens will break free from the hydrogens, right? With water, it's just hydrogen and oxygen stuck together. That'll break up. So, light is, especially high energy light, is really good at breaking things up, breaking up molecules. So how do these complex molecules survive all of that? Well, it turns out that these little cages, whether it's water or carbon or silicates, they make really nice little hiding places for molecules where they can't get bashed with light, right? So you can imagine that there's all these basically little rocky and icy little cores that are like have little caves in them, right? Where individual atoms can go and end up just by chance, but then they start to combine with each other. It's almost like little, like little vices that kind of keep them contained with one another, and they can condense inside of these cold little nooks inside of these dust grains, and you actually get complex chemistry that results from that. So you start to see the appearance of legitimate cores that are housing little droplets of all of these complex molecules, including water, including two hydrogens stuck together, so molecular hydrogen as well, right? So these clouds build up in density. They actually become incredibly dense, and it's very difficult for light to even penetrate to the center of them. And it becomes very, very cold in the center of some of these clouds, right? So no light's able to get in there except for maybe some really weak red light or something like that. That's going to just accelerate the process of condensation of these materials, right? So you're going to get more and more molecules that form deep inside of them just from the simple primitive atoms that happen to find their way there and start to combine, because they're not getting heated up enough to bounce off of each other. They're actually losing heat. The condensation reactions are actually relaxing the atoms as well. They're able to actually lose some heat, is one way to think about it, as they combine into molecules. So that's really interesting. So when we move into start thinking about where stars come from, maybe it's smarter to ask, where do little chunks of stuff come from, period? And the answer is from protected little caverns inside of these tiny little true particles. I don't mean like atomic particles, I mean particles, like stuff, like dust grains, right? Like ice grains. There's true little places where these condensation reactions can start to happen. And we start to see actual nucleation of little droplets and stuff. This is kind of interesting. All right, last thing I want to mention, which is kind of fun, is that there's one other type of stuff that we kind of pointed out already, which are these things called cosmic rays, right? So we talked about cathode rays. These are related, but not quite the same. So what is a cosmic ray? So there's a detectable phenomenon called cosmic rays. What is a cosmic ray? Well, it's basically just an atom that's flying around really, really fast. It's ionized as well, so it's electrically conductive, and it's flying around really, 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 really fast. Now, what's up with these cosmic rays? We can detect them with our detectors, our electric detectors here, electromagnetic detectors. Now, so these are constantly bombarding us. They seem to be bombarding us differently at different periods in time. It's a very fluctuating system. The standard thought is, how in the world does an atom, well, the question is, how does an atom, most of these atoms are in some stage of cooling or whatever, how do you get ones that are flying at, fractions of the speed of light across the galaxy and slam into our Earth? How does this happen? Where are they coming from? Conventional explanation is that they're actually built up from the explosions of stars, right? Now, we don't see a ton of explosions of stars, but we know that it does happen. So maybe it's true they come from this. One thing that's kind of interesting is that when these really fast-moving atoms collide with the Earth, they actually can do lots of interesting things to our atmosphere, one of which turns out to be actually seeding clouds, right? So causing condensation by actually slamming water molecules into each other so they condense. So that's something interesting to think about. I actually talked to this astronomer in Jerusalem who had this really crazy theory that perhaps the reason why we have climate cycles is that as our solar system travels through the galaxy, it spends some time. So this is actually kind of shocking. It's kind of the last thing I want to leave you with. The solar system itself moves through the galaxy. So you guys have maybe looked in the textbook. It says, it has a picture of the spiral galaxy, and it says, you live in this arm of the spiral galaxy, right? The reality is actually our solar system spends time in different arms of the spiral galaxy. We don't rotate with the arm that we're in forever. We actually travel through regions that don't have a lot of stars in them. And so this dude I was talking to had a really interesting idea that what might happen with some of these climate cycles is that when our solar system is in a region with a lot of stars, like an arm of the galaxy, that it's subject to a lot of these cosmic rays, which are actually seeding a lot of cloud behavior on the Earth. He had this really cool experiment where he actually, was able to condense, like in a water bottle, and decondense it just by squeezing it, and talking about how the pressure could lead to the condensation of clouds. And he had this really interesting model. I don't know if it's true or not, but it was very compelling, where the timelines of the different climate cycles actually matched up to the Earth's precession through the different arms of the galaxy, which I thought was really, really fascinating. So more dense regions of stars that we are inhabiting at any given moment, more chances for getting hit by these really fast-moving particles that are flying off of other stars, perhaps when they're exploding at the end of their lives. So that basically brings us to the point where we have a picture of how it brings us to a starting point for how we might be able to make a star, which is kind of where we're headed next. We have a ton of solar wind that's being shot out into interstellar space from all the stars everywhere, a ton of ultraviolet radiation that's getting those atoms all excited all over again. They're engaged in all sorts of chemistry with each other. They're also cooling. They're interacting with all that junk. By the way, where do all these pieces of rock and stuff come from in the first place? Ice. I don't know. It's not something that you're going to find in the textbook, but I will tell you that there's a lot of planets in our solar system, and there's a lot of icy moons. There's a lot of carbonaceous asteroids. There's a lot of silicate bodies. Presumably, at some point in the very distant future, all that stuff's going to get smashed to smithereens, and it's going to end up somewhere, right? So there's a lot of junk as a starting place, and it turns out all that junk makes a really good refuge for condensing gases into little droplets that we might be able to build something out of here in a second. So that's where we'll go. So I'll leave you with that. We'll talk about making